This is Joe narrating a PowerPoint in science. It's from the unit on Earth and Space Science. It's Lesson 5, The Expanding Universe, found on page 536 in the Kaplan book. This lesson talks about the birth and death of stars, the process and result of the death of a star depends on the mass or weight of the star. The Sun is one of billions of stars in the Milky Way galaxy. And the Big Bang Theory tries to explain the origins of our universe. This slide shows a model for the birth of stars. On the upper left, you have a spinning mass of gas that slowly contracts or comes together even closer by the force of gravity. As it spins, it flattens, just like a ball of pizza dough. As you spin it, will start to flatten. The center of this mass may become hot enough to start making hydrogen fuse or combine to form helium. If this happens, you have a star. This nuclear reaction of the formation of helium from hydrogen gives off heat and light. And when we walk out on a sunny day and feel the sun's rays warming our skin, we are feeling the effects of a nuclear reaction on the sun. This slide shows the death of a star, and whether the star becomes a white dwarf, a neutron star, or a black hole depends on the initial mass or weight of the star. On the left here you see a stellar nebula. This is that mass of gas that will spin, condense by gravity into a central body, and that central body, if it's large enough and hot enough, will become a star. Our star, the Sun, is an average star. It's shown on the top diagram. So an average star will gradually, over billions of years, expand outwards. It will then blow off its outer shell, and this will be a planetary nebula as this happens, and what remains will be just the center of the solar system as a white dwarf. We think this will become the fate of our Sun. It will go through the red giant phase in about 5 billion years. When that happens, the surface of the Sun, if you can call the Sun as a gas having a surface, will extend outwards past the Earth. So the Earth will just become a liquid melted rock. Larger stars will follow the path in the lower diagram. They will become what are called red supergiants, much bigger than red giants. They will undergo a massive collapse. As this collapse occurs, the materials collapsing into the center will rebound out and form a supernova. Less massive stars will become neutron stars, and very massive stars will become black holes. In a black hole, the gravitational force is so strong that not even light can escape from a black hole, and that's why they appear dark in the sky. As noted, this is the fate of our Sun. It will become a red giant star, and this sort of shows what will happen to the surface of the Earth. There are beautiful objects in the sky. This is the Eskimo Nebula because it looks like a hooded Eskimo face, but in the center of this object in the sky is a neutron star. Neutron stars are so dense that a sugar cube size piece of a neutron star would weigh 100 million tons. So these are incredibly dense. This is the result of the death of a larger star than our Sun. This is a model of what our Milky Way galaxy would look like if you could get a view from outside our Milky Way, which no one has done. The Milky Way is a collection of stars revolving around a central massive black hole. Our sun is about halfway out between the center of the Milky Way and the edge of the Milky Way, and goes around the center of the Milky Way about every 240 million years. Scientists like to classify things, and they classify galaxies by their appearance. These are all the types. Our Milky Way galaxy is the type seen in the upper right, a spiral galaxy. Our Milky Way galaxy is part of a local group of galaxies, so when you look at our address, it's Earth revolving around the sun revolving around the center of the Milky Way, and then the galaxies in the local group are moving with respect to each other as well. So you can see our Milky Way towards the center of the local group of galaxies. This is a Hubble deep field view of a very small section of space, showing all these objects. All these objects are galaxies, so they're massive each in its own right, and each composed of millions or even trillions of stars, like our sun. The book talks about a brown dwarf. A brown dwarf is just a very large planet, basically, that is too small to heat up enough to start the fusion reaction of helium from hydrogen. So the Earth is shown here on the lower right. Jupiter is the largest planet in our solar system. A brown dwarf would be slightly larger than Jupiter. Objects bigger than brown dwarfs have the potential to heat up enough to start the fusion reaction, which gives off a lot of energy. A pulsar is basically the remnants of a massive star after a supernova. These objects are rotating in the sky. A pulsar is a neutron star that is radiating energy in a distinct beam, almost like a lighthouse. So if you look at these objects on the right angle from Earth, you will see a signal being given off by these pulsars every few seconds, or even every few milliseconds if they're rotating fast enough. A quasar is even a more massive object. It's a very large black hole in the center of a galaxy. Again, as material falls into these large black holes, they give off energy, and in the right circumstances, these can be focused beams of energy. The Big Bang Theory is a fairly well-established idea of how the universe began. It began as a small collection of energy, and the Big Bang happened about 13.7 billion years ago, and it was a massive explosion of space, not really in space. So the inflation period accounted for the very quick expansion of the universe, and has been expanding more slowly ever since then. So objects in the sky are getting relatively farther apart. There are still many things to know about the universe. For example, we think that dark energy is the energy that's pushing objects in space apart. We don't have a firm idea of what that is, but new discoveries are being made all the time. That's it for page 536 in the Kaplan book.